Gilbert Lewis was a famous organic chemist who devised a method of drawing molecular structures in 2 dimensions, which starts with drawing the Lewis dot structure of the individual elements in the compound. And I'll remind you many times, so I'll start now, by telling you that Lewis structures are 2-dimensional images only. They don't tell you about the 3-dimensional structure of a molecule. You can use them to help deduce the 3-dimensional structure, but they don't directly tell you anything about the 3-dimensional structure. Lewis dot diagrams deal exclusively with the valence electrons. After all chemistry is valence electron chemistry. Valence electrons, of course, are the electrons in the highest outermost shell or orbitals of the atom. So if you're looking at an electron configuration, look for the biggest numbers out front. Those are going to be in your valence shell. In metals, these are the electrons that will be lost when a metal is oxidized in an oxidation reaction. And in the reduction part of an oxidation reduction, nonmetals will gain these electrons to fill empty slots in their outer valence orbitals. In metalloids and nonmetals, these are the electrons that will share to participate in covalent bonding. So Lewis dot diagrams are another way of representing the electron, and we've done this a couple of different ways before. We can show them as numbers in the electron configuration. Say for lithium, 1s2, 2s1. We've now located all 3 electrons for lithium. We can show them in boxes. Our orbital diagram, label the boxes and represent the pairing of the electrons in an orbital, where we show that the 1s electrons are 1 up, 1 down, and the 2s electron is alone. So the 2s electron here is my valence for lithium. So lithium only has 1 valence electron, even though it has 3 total electrons. In the Lewis dot structure of an atom, you only show the valence electrons. And that means that all elements in the same column of a table are going to have the same Lewis diagram. So if I grab my periodic table, I could look for, say, oxygen. And if I want to find the number of valence electrons in oxygen, I'm going to start over here and count across. 1, 2, 3, 4, 5, 6. So there's 6 valence electrons in oxygen. But look down at the row below that. If I look down at the next row, the third row, I have 1, 2, 3, 4, 5, 6, and I'm right underneath oxygen at sulfur. So both of those have the same number of valence electrons and will therefore have the same Lewis dot diagram. So you look, and both of these have 6 little dots around them in the same configuration. So actually this is really handy. This means if I know the Lewis dot diagrams of the second row of elements, I know the Lewis dot diagram of everything in the S&P block. Both are in group 16. Both have 6 valence electrons. So how do I do this? Only the valence electrons are shown, so you first count the valence electrons, and you can just count columns across the periodic table, just like I did. Then I distribute them clockwise around the symbol. I usually start at the top, but it doesn't really matter where you start. And when you're starting to draw molecules, you'll discover sometimes it's easier to start on the left or the right or the bottom, just to make your unpaired electrons come out in a way that makes it simpler to draw the structure. So let's say that element X is something else in group 16 that has 6 valence electrons. So I start by putting X, and then since I'm just drawing this by itself, I'm going to start at the beginning and go 1, 2, 3, 4, and now I'm going to pair up 5, 6. So there is the Lewis dot diagram for anything in group 16. So let's try a couple more just quickly to get done. So carbon. Carbon is actually going to be shown as 4 separate electrons, and we'll go into that more in class and how that actually works on a quantum mechanical level. But just follow the rules the way we've done them. Carbon is in group 14, so it has 4 valence electrons: lithium, beryllium, boron, carbon. And so I'm going to draw a big C for carbon. Start at the top, 1, 2, 3, 4. There's the structure for carbon. So now let's try fluorine. And I'd like you to pause the video, draw the structure for fluorine, and then come back and see if you got it right. Okay, so fluorine is element number 9. So if I come up here and count across the periodic table, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, lithium, beryllium, boron, carbon, oxygen, fluorine, that would be 7 valence electrons. So I'm going to have my F, and I'm going to start at the top and go around, 1, 2, 3, 4, and now I have to pair up, 5, 6, 7. And so you can see pretty easily using this Lewis diagram why fluorine will form a 1 minus ion, that empty spot over there on the left of the F, and why fluorine only forms 1 covalent bond. It has 1 unpaired electron to share in a covalent bond. So drawing the Lewis structure of each atom in a compound is where you're going to start when you do a Lewis dot diagram of a molecule. And I really have to say, don't shortcut it. Actually start by drawing out the Lewis dot diagram of every single atom. That way you won't forget lone pairs and you won't have extra electrons magically appearing in your structure. So always start with drawing the atoms, and then we'll talk about how to turn them into molecules.